So I'm going to be talking about a method that we have developed to make relationships between native fish species and flow. And Ryan's talk that's going to follow mine is a similar analysis where he's linking benthic macroinvertebrates to flow, and both of our talks are part of a larger project that I'll be talking about. And so after my talk is done, we'll just roll straight into his, and then we'll both answer questions. So, as news to no one in here, flow modification is prevalent and widespread in California. 95% of streams have altered flows. And a means of addressing this flow modification challenge is through the implementation of environmental flow regimes. And there are a variety of programs that are in place that are attempting to set environmental flows, but California, as we know, is geographically, topographically, hydrologically diverse, and so management needs vary depending on where in the state you might be. Because a variety of groups and programs are attempting to set these flows, coordination between groups and sharing information is often challenging. There are a variety of methods related to setting environmental flows, and so there's some uncertainty on which method might be appropriate depending on where you are and what your stream looks like. And then lastly, balancing between ecological and human water needs is challenging. So there's this need for coordination related to setting environmental flows. So scientists have come together from UC Davis, the Center for Watershed Sciences, Caltrout, the Nature Conservancy, UC Berkeley, SWRCB, and Utah State. And we have developed some methods and tools for establishing statewide ecological flow criteria based on reference hydrology, as well as some recommendations and guidance on developing more refined ecological flow prescriptions when those are necessary. And then lastly, this framework also contains some suggestions and guidance on actually implementing environmental flow prescriptions and translating those ecological flow prescriptions into environmental flows. So an important concept behind our SEF framework that informs all our tools and products is this idea of the functional flows concept. And functional flows are aspects of the flow regime that directly relate to these key ecological and geomorphic processes in riverine systems. And these functional flows are expected to support foundational processes that these native species have evolved their life history with. And this approach was developed in 2015 by Sarah Yarnell and others, and we recognize in our analysis 5 functional flow components. So looking at the hydrograph, this wet season initiation that represents the transition from the dry summer period to the wet period, these wet season base flows, peak magnitude flows, spring recession flows, and dry season base flows. And so these are the 5 components that I'm going to be talking about. And I'm going to keep my analysis at this component level, but when we get to Ryan's talk, he's going to get a little bit more specific in how these components are quantified and how that can be related to ecology. And so going back to the California Environmental Flows Framework, or CEF, I'm going to focus here, and Ryan as well will focus on the step of refining ecological flow criteria using more specific ecological information. So I'm going to focus on refining these flow criteria for native fish. And when we started this analysis, 2 key questions came to mind. So first, if we're making management recommendations based on fish, which species are we going to focus on? Are we going to focus on generalist species, threatened and endangered species? So that step, and then once we've selected these species, what are their flow requirements? So to address this, we've taken an umbrella species approach, where an umbrella species is a species whose protection confers the protection of other co-occurring species, which saves managers time and resources when they're making decisions. And typically, a single umbrella species is used when making management decisions, but because we're doing our analysis at the statewide level, and the state is diverse, we're recommending a suite of umbrella species rather than a single one. So a bit of an overview for how we actually selected these umbrella fish species. First, we used some information about native species ranges to develop some native fish assemblages for each region of the state. And then for those assemblages, we used information about their life history and habitat preference traits to group species with similar traits. Then, to actually go and select these umbrella species based on those groups, we looked at how vulnerable they were to climate change, as well as how much information we have associated with them. And then lastly, we related them to those functional flow requirements that I mentioned at the beginning. So diving in a little bit deeper into the methods. So first we did a spatial clustering analysis. And to do this, we divided the state into 4 regions: the North and South Coast, the Central Valley, and the Great Basin. And then we used native fish species range data from Pisces, and we performed a spatial k-means clustering analysis to group similar assemblages of species within those regions of California. And once we did this analysis, we talked to 10 ichthyological experts from up and down the state, showed them our results to see whether those clusters made sense from a management perspective, and we refined the clusters based on local data and knowledge. So the next step, using those groups, those assemblages from the previous step, was to perform this hierarchical clustering analysis. And we used this fish traits database developed at Virginia Tech, which included trait data for native species in California and actually across the US as well. So some of the traits related to trophic ecology, life history, habitat preference, and tolerances. And so this clustering analysis for our native fish species allowed us to group the most similarly traded species within each one of those regions. Then using those groups, we scored the species based on how vulnerable they were to climate change and how much data we have associated with them. So we selected for the most vulnerable species with the most data available for them. And this is actually how we got our list of umbrella species. And then lastly, we reviewed the literature, recovery plans, standard salmonids, to actually relate these umbrella species back to those 5 functional flow components. And we consulted with some experts to fill in the data gaps where necessary. And for all of our umbrella species, we were able to relate them back to the functional flow requirements that were important for their life history. And where possible, we related them to characteristics. And so characteristics are things like the magnitude, timing, duration, rate of change for each one of those components. So where basically the box lies on the hydrograph and how big the box should be. Okay, so actually looking at the results now of our spatial clustering, remember this was where we used that species range data to develop these assemblages for those 4 regions of the state. So we came up with a total of 16 assemblages, 4 for the Central Valley, and those are in the shades of blue, 6 for the North Coast in shades of pink, 3 in the Great Basin, and 3 on the South Coast. So the next step, hierarchical clustering, remember using that trait data for the species. This is what the output of our hierarchical clustering looked like, similar looking to a phylogenetic tree. But to interpret this, the most important thing to recognize is that the height on the y-axis represents how similar or dissimilar species are. And so if you look at where the branch occurs, that shows you how similar species are. So something like the trout is a lot different from the taco sucker in this case. So this hierarchical clustering allowed us to draw these distinct groups based on traits so that then we could then select those umbrella species. And it's kind of hard to see, but the dashed lines represent groups that we selected then to do the scoring. So this was for the Great Basin, one of the Great Basin assemblages. And if we just zoom in to one of these groups that we have determined, we then did some scoring. So looking at climate change vulnerability, ranging from 1 to 4, where 1 was the most vulnerable to climate change, 4 was the least vulnerable. And then data availability, which also ranged from 1 to 4, one being the species with the most data associated with it. And so we did this scoring and pulled out the species that were the best umbrella species for each group. And then our last step was to then go back and relate each of these umbrella species to those flow components. And so, again, reviewing the literature, consulting with experts, and determining which one of those flow components were important for their life history. So in this case, the Paiute cutthroat trout, dry season base flow is important, and particularly the magnitude, duration, and frequency of that dry season base flow, as well as the wet season base flow and the magnitude of that was important. So again, we repeated it for those groups within each of those regions to get a list of 49 umbrella species for the state. So, like I just said, we took a list of 118 native species, pared that down to 49, which is more usable from a management perspective, especially considering that no 49 occur in one location. This is going to save some time and resources when going and making these flow recommendations. And you'll notice, looking back at this, there's no numbers associated with what these specific flow requirements should be for this given species. And so this analysis really just provides a starting point for future work to determine specific flow metrics needed for each one of these species. And then more broadly, the data types that we used in this analysis, so species range data, trait data, and then some information about vulnerability, those are generally available, so we think that this method could be applied in other locations to other taxa. All right, so with that, I will hand it off to Ryan to talk about how he has related flow and benthic macroinvertebrates.
Hey everybody, thanks Alyssa for setting me up so nicely. I'm going to talk about the benthic macroinverts and flow. And just to sort of caveat or step back for a second, why we're exploring these relationships because with BMI, because really this is sort of the next step, like Alyssa mentioned, in establishing relationships or looking for these relationships between flow and our ecological or our biological data. And really this bioassessment data really provides this really unique opportunity to look statewide at these relationships. And so none of this would, again, to echo what Eric said, none of this would be possible without the statewide bioassessment program and swamp data. So big shout out to everybody that's part of that. It's really important. Why is this important? Well, like I just said, so this is a good way to connect the biology with the hydrology. And ultimately, this is really important for if we are actually going to implement these environmental flows that we're talking about, we need to have a better understanding of what is the specific functional flow metric or component that we can prioritize in management for a given response, biological response. And so we really had two main questions as part of the BMI analysis. One was to sort of explain what is the, using the data that we have, was what are the functional flow metrics that are most predictive of differences at reference sites, so in reference hydrology sites, and I'll talk about that in a second. And then a sort of secondary question is, if we know those metrics or those pieces, what are the most predictive or most correlated things that explain differences between reference and non-reference sites, right? So in our disturbed sort of gradients of disturbance, understanding that is going to be really important for how to manage those different pieces. Okay, so I'm pretty much just going to talk about the first question, so just at reference sites, which is how can we link all this bug data that we've got with a bunch of the flow data that we have statewide, right? And we've got, really this is a sort of a data exercise in how to link these things and reduce them down to something that we can use. And so here's a look at statewide, a bunch of the macroinvertebrate stations, sampling stations. There are a lot, many stations across the state. And at each station, there could be there are multiple samples, right, across multiple years. So overall, there's over 300,000 samples as part of this data set that I looked at, dating from 1994 to 2018. There's different methods, but what's really cool is that because these have been standardized, it's possible to analyze all these together. That's, again, the statewide bioassessment really makes this possible because it's consistent. And then some other folks have worked, the folks at SWRCB have helped develop a number of packages that also make this possible to calculate metrics across these different data. And then the hydrology, similarly, there's over 800 USGS gauges in California, and there's more that are non-USGS. We selected just the reference gauges, and those are based on discussions with folks at the Nature Conservancy and elsewhere based on the Gauges 2 database and a number of other factors. But essentially the light blue dots, or the lighter colored dots there, are the reference sites. And they're the other caveat that we wanted to make sure we were looking at reference sites that had at least 10 plus years of flow data. Okay, so how do we pair these two things? So on the left, you've got all our reference hydrology sites, and on the right, we have our benthic macroinvertebrate data stations, right? And how do we pair these two different data sets? And really what we wanted to know is how can we filter these down to pairs where we're directly comparing sort of the flow relationship with the ecology or the biology index. And to do that, we used this approach using a HUC12 approach was our first filter. So I wanted to know how many sites were occurring in the same hydrologic unit, HUC12 level. So sort of the smallest unit at the moment that we can use. There were about 114 HUCs that had both BMI sites and flow sites, which was actually not as many as I expected given the range of data there. And then what we did was filter to stations that were located on the same main stem as USGS reference gauges. And for that I used the NHD plus streamline data and ended up with about 53 different HUCs across the state, about 250-ish BMI samples. And this covers about 59, well, it ended up being about 55 different gauges. And again, this is just reference data only, right? So these are the most unimpaired or undisturbed hydrology that we can find. And one of the things that was interesting in doing this analysis is I played around with different things, including like spatial buffers, other things to see if we could pair sites. But what you end up having happen is that you end up with I don't know if I have there's a pointer here. So you end up with, so these are the BMI sampling sites here in orange. Here's a reference gauge. And if you sort of buffered like a 1 kilometer buffer, you'd end up selecting potentially this site here or these sites here, which are in adjacent drainages, right? And so if you're comparing the flow relationships, these components or these metrics, they're very specific to a given stream. You probably don't want to be making that comparison with adjacent streams. So that's why we ended up using a streamline approach. And so that yielded a surprisingly few number of site pairs, and I think it really sort of illustrated that we should be thinking about when we're sampling and monitoring, if we do want to establish these flow relationships, that we probably should start prioritizing sampling near gauges where possible. Now again, there's a whole set of data that we're in the process of pulling for non-reference gauges, and so that might expand things a bunch. But as far as the reference hydrology, we actually, if you look across the state, the coast is fairly well represented, but the Central Valley is not. Northeast California is completely unrepresented. And then we have a really nice density in and around Tahoe. So anyway, something to think about. And then we wanted to link this stuff temporally. So we have this flow data, we have this bug data, but those could encompass different time frames. And so what I ended up doing was using 4 different hydrologic data sets. And to do that, we calculated or used the metrics, these flow metrics, which I'll talk about in a second, for annual, so making sure that the benthics data is from the same year that the flow data is from, so a one-to-one relationship. And then a lag of 1 year and 2 years, so looking at the flow data from 1 year prior or 2 years prior. And then finally looking at the whole period of record for the flow against the biological data. And just to reiterate what Alyssa was talking about, I'm going to sort of go through, we looked at 34 metrics. This sort of number shifts a little bit, but I'm going to break down kind of a number of the metrics that we looked at within each of the flow components. So the fall pulse flow is sort of the first flow that occurs, and there are metrics associated with duration, magnitude, timing, so the date of when that peak event occurred. Whoops, sorry. Peak flows, which included magnitude, duration, frequency, and timing across these different recurrence intervals. Wet season base flow, which also magnitude, timing, duration. You're starting to see a pattern here. And then spring recession, magnitude, timing, duration, and rate of change. And then finally, the dry season base flows, which included same thing, magnitude, timing, and duration. So for each of these flow components, there are a subset of metrics, specific metrics that we can use to compare against our response data, our biological data. And what's really cool is because we have this statewide data set, it's really rich and there's a lot of information there. There's a whole bunch of different metrics you can calculate, as most folks are aware for benthic macroinvertebrates. We modeled these 4, although I did play around with a few others, and there's definitely more opportunity to focus on additional metrics. But we picked these because we felt like they're most representative and useful across the state: the CSCI percentile, Shannon's diversity, percent intolerant, and the MMI, which is the multi sort of metric index that goes into CSCI, but it represents more of the functional feeding groups and functional groups. And then what I did was took all that data and crunched it into these boosted regression trees and ran about, 400 different models that just finished like on Monday. So what this ends up doing is it allows us to pull out the metrics that are most predictive or most informative in describing the variation in the bug data, right? So which flow metrics are most informative for the biological data? And boosted regression trees have been used pretty extensively now in ecology for describing these sorts of things, because they're really good at pulling out the sort of top metrics or top informants in the data, and they're really robust to missing data, different data types. They're nonlinear, so they can do a really good job of pulling out basically the messy things that we see inherently in ecological data. So the results, as you can see what this generates, these are bar plots of the relative influence, so the percent scaled from 0 to 100% of a given metric, flow metric, on sort of the benthic macroinvertebrate response, the data, right? And so what you're seeing here is across the top, each of those columns is the different flow data sets, the annual, the lag, and the period of record, right? And then on the y-axis there is all the different specific flow metrics, so individual flow metrics that we could pull out and look at those relationships. And this is across all 4 of the different BMI responses that I showed previously. So if you were to look at this, you could say, the annual data for flow, and what's most interesting to me when I first saw this is that all the flow components are pretty well represented. Right? This is like the top variables for all the models across everything, and you still see a representation of all the different flow components to some degree. And the other thing is that shifts depending on the flow data set used, which is interesting. When Dave gave his talk earlier that there's potentially these drought effects, unsurprisingly, but we're actually seeing that now in the actual hydrology, the flow metric data, which is really cool. So we could pull this out and actually explore this much more in depth. And really look at those relationships for a given region, for a given area, for a given metric. And then if we look at let's just look at the annual data, but now we'll look at, now the columns are the different BMI responses, the CSCI, intolerant, MMI, and Shannon's diversity. And so suddenly you can start seeing some different patterns where for the annual data, some of the top predictors are the peak magnitude, the 2-year recurrence interval for CSCI. For the MMI, the functional feeding groups, it turns out like the wet timing, or the timing of the wet season is really, really important. Same thing for diversity. And so you can start compiling these across different ways and slicing and dicing this data in a lot of different ways, but I think what's really important is to look at this is we can use this to prioritize different metrics if we're sort of building an environmental flow regime. And then if we look at the lag data, again, against the different response, the BMI response, what's interesting is suddenly the things that pop out a little bit more are the peak frequency. So how many times in a given year do you have a 2-year event or a 5-year event? And that's really important actually for the functional feeding groups, the MMI percentile, which incorporates that. For the intolerant species, the recession timing becomes really important. So the recession timing from the 1 year prior, which is pretty interesting. And diversity, the thing that popped up was the timing of a 20-year event in the year prior. Lag 2, suddenly the things that start to pop up a little bit more are much more on the fall pulse flow. So when was that fall pulse occurring, and how big was it? What was the magnitude? And similarly, the duration of the peak flows in the prior 2 years ago. So these become interesting in a sort of a disturbance sense, right? Like how things were disturbed in the year or two prior become really important for the life histories. And then the other thing you can pull out of these models is we can actually look at the relationships across these different flow metrics. So if we know there's a certain flow metric that explains a lot of our variation in our data or is most predictive of a given thing, we can pull that out and look at it specifically to see what is the relationship. Is it positive? Is it negative? And we can do this across all those different flow metrics for whatever response we're interested in. And so what this does is it essentially shows the average change in the flow, the BMI response if we vary the flow parameter. So you can look sort of across the range of whatever the flow parameter is and see what the relationship is. And so I pulled out, just as an example, the lag1 data set, the MMI percentile, and you can say, well, there's a fairly positive relationship with peak frequencies, 5-year recurrence of a peak frequency up to about 4 or 5. Sorry, the point over here. There it is. So, at about 5 events, a 5-year event that happens more than 5 times in a given year, then you start seeing a response where it actually has a negative impact, right? So that's how you'd interpret that. And you can also use this to quantify the uncertainty, right? So we can do this across all the different data points that we have and actually say, how much uncertainty do we have around this variable, outside of this sort of range, which is helpful. So it gives us a sense of how much can we use this up to a certain degree, and where are the data gaps in our data sets. Okay, so to me, I feel like this has been really interesting, and I'm super excited about being able to use this in the framework, the CEF framework that Alyssa mentioned, because I think it really gives us a pulse on sort of how we can look at things regionally, we can look at things on a statewide level, and really get a sense of what are these important variables from a flow standpoint that we should be prioritizing. And so, again, this is preliminary, we're sort of still mining all of the stuff that's in this, there's a lot of information, but if we were to sort of summarize some of the main things, I think it's hard to manage for the overall, the natural flow regime, but we can use these metrics to inform actual flow ranges or periods. And so using this functional flow approach requires understanding, like, is there this range of variability? And there is. We have a good sense now that there's a range of variability at reference hydrology sites. we can use that now when we compare the second part of our analysis, which is going to look at the non-reference sites, right? And that we've identified which flow components or metrics are most important in explaining the variability in our data. And then I think in particular from a drought standpoint or these big shifts in climate that we're going to be experiencing, these whiplash effects, there is definitely a lag effect. We're seeing that in the data on a statewide level. So considering how we are going to select a given metric or how we're going to manage a given system, it's something to consider, and this is one approach that might allow us to tease out some of those details. And like I said, I think this is ultimately one of the cool things about this is it will allow us to prioritize, in this case, metrics, individual metrics that might be important to implement or protect in a given flow regime. So now I'd like to bring Alyssa back up for our overall conclusion, which is pretty brief. We feel like this has been a good approach for two different data sets. The fish data we have at a flow component level, the bug data we have now at a metric level. And so that allows us to apply this functional flow approach statewide. You want to take that one? Okay.
Yeah, so like Ryan said, and I mentioned earlier, this is really a starting point for additional quantitative analyses that are needed to develop those specific ecological flow prescriptions. And what we've done is we provide some guidance on which functional flow components or metrics should be prioritized when we're making those management recommendations. So with that, we are happy to answer any questions.
Those are really good presentations and an excellent way to start mining that data that's coming out of these bioassessment programs. I think I have more a comment than a question, and maybe you can talk about that as well, but it seems to me that it argues for the importance of getting really consistent annual data collected at some subset of these reference sites so that you can parse a lot of these data with even greater precision.
Yeah, I think that's a great point, and that's something we have identified a few of these where we do have pretty good replicates, across our samples over multiple years, and that's definitely something we'd like to explore. And I think in particular, in doing that in a comparison from a reference to a non-reference would be really interesting to see, which of the flow metrics are most responsive and which aren't, if you're comparing across those different flow regimes.
Hey, fascinating talk. Very well done. I wanted to ask you a question about basic flow. I'm in the Colony River watershed. I live in the Colony River watershed. And so I read a lot of the technical and political documents. And the base flow is, in some documents, is 60% snowpack. And a lot of people say snowpack is our biggest reservoir, but it's actually soil water that's a bigger reservoir. And I was at a conference where I heard a scientist say that the base flow was 40% snowpack in the upper Macaulay River watershed. And that's a great variation. Of course, it's going to vary a little bit. You expect climate change to affect the snowpack, but it would be road construction that would probably affect the soil water and the base flow. And I noticed that there was changes over the years in the California Water Plan Update, which is a legal document in the Water Code. In 2009, for example, they took a stand against hardscapes across California in order to preserve the water cycle. And that has been gradually taken out of the water plan. I just wondered, what was your opinion on the factors that would affect the base flow? Is it road construction? Is it snowpack? Well, should we be more concerned about the construction of roads and how they're being constructed? Will that affect the base flow overall?
I think that's an interesting point as far as, we were more interested in understanding the base flow as a sense of like, it's a point in the hydrograph where the flows have dropped where you're hitting that sort of low summer flow, and so you can measure the magnitude or the timing, and it's more, I think what's interesting is in this analysis, we can look at any point in flow and less a point in time to look at, what that effect might be. But I think there's a whole, if we're looking at a statewide data set, there's a whole bunch of different factors that could play a role in what proportion of water makes up base flow, right? Depending on where you are, if it's groundwater driven, snowmelt driven, rain driven. And so I think I specifically don't necessarily have an opinion on that because we were looking more at linking the flow data at reference sites with the actual biological data that we can do. But I think from a management standpoint, those are all factors that folks are thinking about, certainly.
But you have to take into account those factors if you're going to make an ecological prescription. And so it should be of concern to you to decipher some of these background effects.
Right, and so that's why we're looking at a statewide level to sort of pick out what is, across all that different variation, what are the most important things, and then regionally we can dive in and then look at that same data and see how those things are different, right? So then for a given region you could say, hey, maybe in this area these things describe that more effectively than others. So yeah, certainly it's an important thing to consider.
And I think it's also important to mention that these are just two ways that you could go about refining your ecological flow criteria to get to those prescriptions. And when you get down to the more site-specific scale, looking at things like roads is definitely something that you consider.
Great presentations. Thanks for that work. It's really gratifying to see the applications to these data sets. So I'm really interested in the temporal impacts here, the perspective of looking at the linkages in current benthic metrics and the prior 1-2+ years history. I'm curious if you've thought yet much about going further back in time than 1-2 year logs and lags, and if so, then how have you thought about looking at some type of cumulative press disturbance or some way of quantifying, not just what happened 3 years ago, but what happened over 1, 2, 3, 4 years? Because I think it's that perspective that we're going to need to have to make predictions and think about the impacts of these types of stresses long term. Curious about that. Thanks.
Yeah, I think that's a great question. It's sort of like the death by 1,000 cuts, cumulatively. So I think, yes, I think that'd be really great in this data set. I think it's possible to start getting at that. I'm not quite sure exactly how to sort of quantify that yet, but I think it's possible, and because of the data set that we have and now moving forward thinking about that, I think it's certainly something we should be looking at, because cumulatively if you have drought, then, like we're having, like I said, this sort of whiplash where you can have a drought impact and then a high flow, high disturbance year, and then, a drought year again, or whatever it is, that's certainly going to have a much bigger impact cumulatively than any one of those events. So yes, I would like to do that, and haven't quite figured out how yet, but we will work on that.
I'm curious if you can explain how you characterize the wet season base flow. I feel like there's so much like peaks and drops, and so what part of that do you use to say this is the wet season base flow?
Go for it.
So I think wet season base flow we defined as sort of the period between that wet season initiation or the fall pulse event all the way up into the the start of the spring recession, and those peak magnitude flows can occur during that time period, so there is some overlap.
So is it like a one flow that you say? Can you use the microphone? Is it one discharge or like this? It's 50 CFS or something?
So we didn't have time to get into a lot of details, but one of the things about those functional flow metrics that Alyssa and Ryan talked about is we sort of have standardized ways of calculating those. And so the first step is, as Alyssa said, is we bracket a time period, so what is the winter period? And we define, you saw in the hydrograph she showed it as a box, so we define sort of a duration and a range of magnitudes within that time period, what is sort of the range, and that's based on all the gauge data around the state, so we have some understanding of the natural variability in the system, and so we can define a range of magnitudes and a range of durations that typically characterize that winter baseflow period and keep that separate from, say, the summer baseflow because they're functionally doing different things in the system. We have time for one more question before we move on to Thomas.
I honestly didn't see who's acting.
Clinton. So my question is related to fire impacts, and a lot of times we consider fire impacts to be driven by pollutants and habitat changes from runoff. Do you have any stations that are co-located with burn areas where you can look at changes in the flow dynamics post-fire associated with recovery?
Possibly. Again, I was just looking for these, we were trying to create these reference hydrology sites across the state, but I think it'd be really cool. Again, this is where this sort of statewide data set becomes really valuable because we can now parse out, these things based on fire, right? Look at pre-post fire, how many years fire has a given site been there. So yeah, I think it's something we could get at, but no, I haven't done that specifically.
Chad, I think your question relates to what Pete was talking about as well, sort of this taking the broader perspective on some of these things. So thanks to Ryan and Alyssa for